This is the solution to problem number 11 in spring 2018. For this problem, we have a merry-go-round with a radius of 3 meters, and it's rotating at an angular speed of 4 radians per second. So that's an omega naught. That's the initial angular speed is 4 radians per second. The merry-go-round is slowing at a uniform rate for 20 seconds until the point where the edge is going at 3 meters per second. And so then we're asked, what's the magnitude of the angular acceleration? So this problem, we use this formula that relates the angular acceleration to the angular speeds. It's analogous to the linear equivalent, which would be Vf equals v0 plus at. It's worth pointing out that this formula only applies to uniform angular acceleration, just as the other one applies to uniform linear acceleration. And it also makes sense because the acceleration is the rate at which the velocity is changing, and so the final velocity is the initial velocity plus the rate at which it's changing times time. So anyway, this is the formula, and we know omega naught, and we know t. We're solving for a. The only thing we need is omega f, and we're not given that. We're actually given vf, the velocity at the edge, which is 3 meters per second. So the final velocity at the edge is 3 meters per second. And if we want omega f, we just have to take vf over r. That's just the relationship between the angular and the linear variable. So we get 3 meters per second divided by 3 meters, and we get 1 radian per second is the final angular speed. So if we plug this all in, we get the final speed of 1 radians per second equals 4 radians per second plus alpha times 20 seconds. And when we solve for alpha, we get negative 0.15 radians per second squared. And the problem's asking for the magnitude, which is 0.15. And so the solution is a 0.15 radians per second squared.